we're all together. Just so as a reminder, just because it could be useful information, if you go to the our course site, and I had created like a small assignment. It's like a fake assignment, but it's just like if you, it's like a mid-semester poll, just to get like a sense of like what topics you have found more complicated or more interesting and things like that. So if you have time to complete it one of these days, that would be helpful. For example, it seems like some of you like the graph stuff, so I would try to see if there's another way, if there are other ways to mention that again, like other things about graphs. Oh, you can just type it directly into Canvas. Yeah, and it can be very short, like has like can be a 3 or 4 lines, like doesn't have to like just whatever you want to say. Like for example, like if you found the book useful, in case you were reading it, or if you have watched some of the YouTube videos, like you can just say anything that you want, but it can give me like a better sense of what topics to emphasize or de-emphasize next time I teach this next semester. So it's more for the future generations, right? Sometimes one needs to do things for our future successors, not for ourselves. Um, so I mean, just to keep it, if you can check it out, like just to see. Let's see. But yeah, I mean, like you can just, I think it was set up as just typing because I was not expecting you to like upload like a 1-page document. It can be very short, what you want to say. So let me share the iPad. Is that okay? Are we okay from so far? So far, so good. The idea for today was to continue talking about the Euler characteristic, but from a perspective which is more aligned with the point of view that's taken for the Poincare conjecture. So again, remember that at least if you had like a surface, if you had a surface, there was a thing called the um, genus G, which is like a fancy name of saying number of holes. So here, like you would say that the sphere has genus 0, that the torus or the donut has genus 1, that this one has genus 2, that this one has genus 3, and so on. And then the idea would be that the Euler characteristic, which again we sort of computed like by looking at graphs. But the point is that the Euler characteristic, at least for surfaces, you can think of it as like it does give you 2 minus 2 times the number of holes. Okay. So for example, for the sphere, since the genus is 0, 2g becomes 0. And so the Euler characteristic of the sphere was 2, of the torus or the donut was 2 minus 2, which is 0. For this thing with 2 holes, I don't think there's thing specific name for this, or I remember it. For this, it would be 2 minus 4, so it goes -2, and things like that. So uh, at least this gives you like an interpretation of like the Euler characteristic in terms of something about the surface that you're working on, and that's nice. But today we're going to talk about a little bit about a different perspective about the Euler characteristic, which gives it which makes it a lot more powerful than what it looks like at the beginning. Okay. For that, we need just to go over a couple of like terminology. So let's start with our friend, the XY plane, right? By the way, I mean, like as I said, like really this course, like I'm trying to say in things in such a way that you don't even know what calculus is, right? Um, like I haven't really used like any formulas, right? Like any fancy formulas, if you think about it. But I'm just curious, like maybe people had already answered this before. Has everyone, like just to know what to say or not to say, has everyone uh, talked about like, has everyone taken like a, say like a calculus class in high school? If you haven't, that's fine, but I'm just curious, is there anyone who hasn't taken like a class that talks about derivatives and things like that? Or has everyone done so? Oh, yeah, let's try. This will be my first time doing a poll. Let's see. This will be fun. Anyone knows where to do a poll on Zoom? Let me check. Oh, polling. Right. How? Uh, oh, edit. Or, oh, calc. Is there, do you have now the option to take like a poll? Oh, wow, this is so fun. This is interesting. I didn't know that's how you did it. Huh. Right. Well, right. I suppose also you could have emailed me that on the privately, but that's, I agree that that helps. Yeah, but I mean, I usually okay, I trust people at showing up out of their goodwill. Hmm, I think there's 5 of you who haven't completed the poll. I mean, again, like it's totally fine if you haven't taken it. I just was curious. At least 75% have voted yes. Um, Maybe let's just wait a couple of seconds. Okay, good. Let's 16 out of 20 say yes. Uh, but good. I mean, like again, like I'm not going to say anything major about calculus, but I was just curious. I think I'll um, end the poll because it could be distracting. So good, good. I'll stop it here. But thing, yeah, yeah. Good. So let's go back to the iPad screen. So I don't know the answer of 4 of you, but at least I know now that. But even if you haven't taken calculus, surely you remember Pythagoras theorem, right? So imagine that you had a point P here, comma B, and you had a point Q, which is C, comma D, okay? And you know, there, you can make this right triangle. So here, let's say it was a value A, here's the value C, here's the value B, here's the value D, right? So what are the sides of this triangle? One side has a length C minus A, and the other one has length D minus B. Is that making sense?
Yeah, that makes sense.
Good, good, good. And then by Pythagoras theorem, right? Like you have the hypotenuse, right? And then by Pythagoras, this has side. I mean, this has length C minus A squared plus D minus B squared, and then you take the square root of that, right? So that was what the statement of the Pythagoras theorem, and in a way you can like think of that as, you know, on the plane, if you have 2 points, right, the shortest path between 2 points is a straight line, right? So let me just write that. So meaning that if you wanted to take a road trip from P to Q, right, and you want to spend you want to spend the least amount of fuel, and hence save you money, like you would take this route through the hypotenuse, assuming that there are no obstacles, right, like that there are no buildings, nothing that would prevent you from taking this line. But if you made like a tiny deviation from this line, like, you know, maybe you are driving through along this line, but then you see a gas stop and you go to a Denny's or a Burger King or whatever, and then you go back to Q. Like this other path would have like a longer distance, right? So in general, the path of least distance between 2 points is the straight line. Is that okay? So now, and like in a sense, like this is almost baked in, and so you would say that in general, I mean, this is where like, well, I'll say this later, but you would take the distance. So you would, what would the distance between P and Q be? So the distance between P and Q is, which I will call dist between P and Q, is just like the length of this path, right? It would be just like C minus A squared plus D minus B squared. Is that making sense? So this is just, notice that this is the length of the straight line. or the segment, the straight segment connecting P and Q. Is this making sense? Good, good. Now, now here comes the pragmatist in you. Oh, by the way, right. Before saying that, uh, what is a circle? Like this will be something to keep in mind. Like, so you have a point A comma B, and you want a circle radius R. What's the definition of a circle? Anyone wants to say? Oh, good. You gave the answer, the right answer. I was hoping that someone was going to say first this. No one like, right? That's the equation of a circle, right? Assuming that this is like the point X comma Y, right? But that's not the definition of the circle, right? Like there's a slight difference because the definition of a circle is, as it was Alex said, it's just like the points of which who are at a distance R from this point A comma B, right? Is that making sense? And it's just, it happens to be the case that if you look at the formula for the distance, because of Pythagoras theorem, right, like that just means that you're saying that the distance between the point X comma Y and A comma B has to be R. But then if you look at this formula for the distance, right, it would be like X minus A squared plus Y minus B squared equals R, and then you square both sides and you get X minus A squared plus Y minus B squared equals R squared. Is that making sense? But it's sort of like this formula sort of appears, right? This formula, like this equation is like a consequence of the definition of what a circle means and the definition of and the formula for the distance function, right? So this equation, this is this can be found from the, is that making sense? So it's not, I mean, you are not strictly speaking defining the circle by this equation. It's just that from the definition of the circle and the Pythagoras theorem, you find that the equation of the circle is this. Is that okay? Good. Now, this may all seem like, why are we saying this? And so here we come to a slight shift of perspective, which will be interesting for what we're about to say in a couple of minutes. Let's talk about what's sometimes called taxi cab geometry. There's this book about it, a Dover book. So it's like $5 if someone wants to read it. It's quite cute. Uh, uh, and again, like the idea of the of this taxi cab geometry game is that it's saying, okay, right, we had like in order to consider the distance between these 2 points, we sort of look at the hypotenuse, right, of a certain right triangle you can build out of these 2 points. But like strictly speaking, right, if you are a taxi now you could be an Uber or Lyft driver, like this was written a couple of decades ago, this book. So now if you're a taxi, right, like you don't really care about this distance, right? Imagine you're driving on in New York as a taxi driver. Like why do you want to know this distance? Like when have you seen like a taxi drive along a diagonal, right? Like that's not how streets are made up, right? So like usually the motions that if like your city was planned accordingly and it was not just created randomly and chaotically, like usually the motions that like you would just be allowed to do are like just left, right, north, like east, west, north, south, right? Like you can never move along diagonals. Is that making sense? And so like in terms of like how much fuel you're spending, like knowing that this form like this distance is not useful for you, what actually you will look like, right, are like at these two sides of the right triangle we had made before, which had length z minus a and d minus b, right? And like this is like the type, like if you were a taxi driver, right, assuming that you can only move horizontally or vertically, like, and if you wanted to reach this point sort of in the most efficient way, since you're not allowed to move along a diagonal, like probably like what you would just try to do first is just like move first horizontally and then vertically, right? And so you can talk about the distance, the taxi distance between these points A, B, and CD to be like just like the lengths of these two sides, right? It would be C minus A plus D minus B. Is that making sense? Again, because like for this pragmatic purpose, like that's really like the distance that you would sort of be allowed to travel. In fact, like strictly speaking, if you like, I'm placing here this other point, the second point, in such a way that like C is bigger than A and D is bigger than B. In like the true formula, right? Like because I could have put this point, like say in the fourth quadrant or the second quadrant or the third quadrant, and then you have to think of a little bit about the signs. So the distance formula, the distance in the taxi world from AV to CD, like would be like really like the absolute value of these numbers, just because like again, like depending on where you located the second point relative to the first one, like some of the some of the entries can be like if for example if you had put CD to the left, like you have to be a little more careful with the way in which you computed the this side, the length of that side. So like really like it has like an absolute value. Is this making sense? Good, good. And so for like, and you might say, okay, why are we doing this? Like, I promise, like this will be more clear in a second. But like, just to like make this a little bit more concrete, like what I'm saying is that, like for example, if you look at the origin at the point 0, 0, and you look at a point x comma y, right? Uh, then the taxi distance, right? Like what I'm saying is that like the taxi distance from the origin to this point x comma y would be the sum of these two sides, which in general, I mean, would be like x plus y in absolute, like the absolute value of x plus the absolute value of y, so that in case I had chosen the point x comma y on the second quadrant where x is negative, the absolute value makes it clear that it was like a positive, like turns it into a positive number so that the distance is actually positive, right? Because we care about the length of the side. So like the absolute value sort of takes care for you about this an annoying fact that the point could have been located in the other quadrants. Is this making sense? Good, good. And now, what would be the a circle of radius 1 with respect to this distance? What is a taxi circle or circle cat? I don't know what would be the best way to what I mean is that now you look at all the points, right? This would now consist of all the points. Uh, say, like I'm talking about, like say the let's talk about the circle, like centered at 0, 0 with say radius 1, just to make it uh, easy in this perspective in the taxi world. So it would consist of what? It would consist of all the points x comma y, right? Whose taxi distance from 0, 0 is 1. Is this making sense? And now, what do you think? Do you think one should get the same equation as before? What do your instincts tell you? So what's the equation? Like the question is, what's the equation of this circle, right? Or how does the circle look like, right? How does this look like? That's what I'm asking. What do you think? Do you think it would look as a circle that you know, the regular circle that you know I care about, or not? Oh, wow. Yeah, yeah, good, 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 good. All my traps have been defeated so far. Right. Do we agree that the equation of a circle in this world would be absolute value of x plus absolute value of y equals 1? Is that making sense? Because that's just like precisely the distance from a point to, again, this is a taxi distance from 0, 0 to x comma y. Is that okay? And so that's like the actual equation. So if someone asks you in the taxi world, what's the equation of a circle? This would be your answer, right? I'm just saying like we're trying to figure out how does that look. And so for example, when you're in the first quadrant, right? When you're in the first quadrant, right, both x and y are positive. So you see like the equation of like the distance would be just become x plus y equals 1, right? Anyone recognizes this equation? That's the equation of a line, right? Uh, this is like the line y equals 1 minus x, which again, hopefully everyone have seen this before. On the other hand, like say for example here, where x is positive and y is negative, this really becomes like the equation of the circle becomes like x minus y equals 1. And so again, this is like x minus 1 equals y. And so you get this other part of the line. And then, I mean, the other two cases, the other two quadrants are more or less similarly solved. So you get like this square, like just rotated 45 degrees. Is this making sense? So this now thing that was you would usually call a square, now this deserves the name of a circle, right? So now this is an actual unit circle in the taxi world. Is this making sense? So why am I doing this? Because I want to sort of convey two morals of this story, so things to think about. Um, so two things to keep in mind. Right? That's exactly the same XY plane, right? The plane, XY plane that you have always known, right? It's possible you're free to define different notions of distance on the same, exactly the same XY plane. So like the first thing to realize is that on the XY plane, there's more than one way to define what you mean by the distance between 2 points. And once you have chosen a definition of distance, you can sort of like think about how geometric shapes would look like according to this definition. So for example, how a circle would look like and things like that. So after you have made a choice of distance, um, things like circles or other geometric shapes, objects may look different depending on this choice. May appear different. Is that okay? Is that making sense? So far, so good. Good. Now, let's talk about what happens on the sphere. And this will take us into the realm of what's known as spherical geometry. So let's talk about this. So on the sphere, right? And everyone can see this like sort of pink dot, right? Everyone see it? Good. So imagine that this is like a point on the sphere. Well, like for it has been made very big for theatrical purposes, but it's just like a point. So you want to find the distance between this point. Does everyone see that? Everyone sees the two pink dots, right, on the sphere. Uh, and so you want to find the distance between these two pink dots on the sphere, right? Oh, this looks like a very ugly sphere. Oh, this looks better. Right. So we want to find the distance between these two dots on the sphere. Is that making sense? Um, so again, like that would mean, like for example, imagine that like Earth had like really honored its name and were entirely without water, right? I mean, there's like it's only land, so you can always drive um, on the Earth without worrying about sinking or anything. Then like that would be like I'm asking you, like imagine you want to make plan a road trip from P to Q, but again, you want to spend the least amount of money on this road trip. So like you want to spend the least amount of fuel. So maybe you can choose that path, or you can choose this path, like that does something weird and gets uh, does like a strange exploration of the planet, right? And maybe you choose something like this, right? So like there are potentially different paths that you can take from P to Q. And essentially the distance between P and Q should be like sort of like the length of the path, of the shortest path between the 2 points, like similar to what we did with the straight line and Pythagoras theorem. So like the distance between P and Q should be the length of the shortest path between P and Q. Okay, and like the easiest way to write like down the formula would be like like the sphere is sort of like, again, you are trying to find like the distance between these 2 points. Like the sphere is like has a lot of symmetry, right? So like essentially like the distance should be unaffected. If you imagine you were God, like you can just start rotating the sphere. And the point is like computing this distance should not depend on where, like, on how you rotated the sphere, right? Like the distance between these 2 points has sort of like remained the same even as I rotated the sphere. So there's no one gets hurt if you just assume that one, like if you rotated things so that one of the points became the North Pole. Is that okay? I mean, it's just easier to state what the formula is supposed to be if you just take one of the points to be the North Pole. I mean, it's not that different, like difficult for the other cases, but that would be enough for ours, what we're trying to do. So let's say that the point P was the North Pole. Okay, is that making sense? And like the other point Q is somewhere around on the sphere. Like you can put it below or above the equator. Like I'm just going to put it here above the equator just because it's easier for my purposes, drawing purposes, right? So far, so good. And then there's like, there's a longitude, or what's the other name for this? Like a meridian passing through from P, passing through Q, right? This is like called like a line of longitude, right? Is that making sense? And the distance between these 2 points is essentially the length of this arc of the meridian, of this piece of the meridian. It's not the entire length. It's just like this segment that I didn't write like as a broken segment. So it's just like the distance between P and Q on the sphere is just the length of the piece of the part of the meridian of the Is that okay? So whatever length this curve has, this piece of meridian has, that's the distance between these 2 points. Let's try to test our intuitions to see if we can pin down this formula correctly. Um, so the idea is that imagine that you had like a sphere of radius r, meaning that like from like center of the origin. So any point is at a distance r from the origin. Okay. So if this is the North Pole, this is a point Q, and let's say that you choose a point on the equator. Right? Um, what do you think the distance between P and Q should be? It should be the length of this meridian stuff connecting the 2 points, right? Like, so there's like a meridian or a longitude connecting P and Q, right? I'm asking what should the length of that meridian or that line, this curve be? Anyone wants to take a guess? Good. Do you want to say how you thought about this? But yeah, that's the right answer. Great. Yes. Right. There's like a circle. Like you can imagine like there being like a circle, right? There's like a circle of radius r here. Does everyone see like that there's sort of like an orange circle of radius r connecting the pink and green dots? So what right, like the right guess is like that's a quarter of the circle, right? Like the distance between P and Q, this segment is a quarter of that circle. So this is like there's a 1/4 of the length of the circle passing through P and Q. But this is a circle of radius r, right? So the distance, right, from P to Q is 1/4 of 2 pi r. And so that's pi r over 2. Is that making sense? So I'm saying that this has this segment. Let me color it. This segment has length pi r over 2. Cute, cute. And now here we come to the interesting fact, right? So what's a circle? So this is the distance on the sphere between P and Q. What would be, here's a question. What is the circle centered at the North Pole of radius pi r over 2? With respect to this distance? What is that circle? The red dot would be the center of the circle, right? So the red dot uh, is we're getting close. The red dot is the North Pole. So I'm saying like you look at the North Pole, right? Okay, let me draw the picture again. But good, good, good. This is confusing. This can be confusing. So I'm drawing the North Pole, right? P, and I'm looking at all the points Q, right? Whose distance from P to Q, right? That's a circle. Remember, a circle consists of all the points whose distance from a given point is fixed, right? So I'm looking at all the points whose distance on the sphere between P and Q is pi r over 2. What would that correspond to? It is the equator, correct? Good. Is that making sense to everyone? Yeah, well, in this case, it would be like the biggest latitude, right? Like because of this particular choice of radius. But yeah, it's like but if you had chosen a different radius, it would be a different latitude. I agree. Yeah, yeah, yeah. So what I'm saying is that if you choose any point Q along the equator, right? Our computation from before had said that this had that this distance was pi r over 2. So this equator should be from this perspective, this equator would be called a circle center at the North Pole of radius pi r over 2. So this, like from the sphere point of view, right? So according to the sphere, the equator uh, is a circle centered at the North Pole of radius r, which is pi r over 2. Is that making sense? But like, just think about this for a moment. This looks like a circle, right? Like this actually looks like a circle to our eyes, but it now has this weird feature where the center of the circle is not really where we would call the center to be, right? Like the center of a circle, like the circles we know and care about, like would have been here, right? But sort of from this perspective, from the sphere's perspective, the center is like somewhere else. Is that making sense? But still, you know, like uh, the length, like the length of this equator, right? What's the length or the circumference of this equator? So what's that circumference? Well, this is still right. This is still like from our, I mean, from the outside world. This is like this still has circumference to pi r. Like that hasn't changed. The length is still the same, and so that means. But how does that compare to? So let's call this C for circumference. How does this compare to 2 pi little r? And see, where am I getting this r so big? Yeah. Oh, okay. Right. So what this is saying is that the circumference in this case is less than 2 pi little r, right? Is that making sense? This can be confusing. What I'm saying is that you cannot use like, let me say it a different way. If you use this radius to compute the length of the circle, you will find the wrong answer. Is that making better sense? So you cannot use, like, let me write it this way. So you cannot use, you can't use 2 pi r with to find the length of the circle. Is that making sense? And so maybe you have heard this. Actually, yeah, exactly. Good, exactly. So this is like one of the, like, maybe have you heard about non-Euclidean geometries? So this is like we're secretly playing with a non-Euclidean geometry. So this is like an example of a non-Euclidean geometry, where like say like right as we were discussing, like I think it would be better to say like this. Like for example, if you look at the circle from the North Pole, right? As we were saying, like that would be like say some latitude, right? Like not necessarily the equator. It depends on the size of the circle that you're choosing. So this would be like this would have a certain radius r, but now the radius is sort of measured from this North Pole through a meridian. So this would be like this would be like a circle of radius r. But now the circumference or the length of the circle, but now the circumference or length of the circle is less than 2 pi r. Is that making sense? And like, for example, from this perspective, like the thing is like from this perspective in the world of the sphere, these segments, these meridians or these longitudes sort of deserve every single right to be called like lines, just because they're like the curves that connect the 2 points in the fastest way. So like what I'm trying to say is that you could choose like, for example, like you could choose the North Pole and 2 points on the equator, Q and R, and these meridians, these two meridians together with this piece of, so these two longitudes together with this piece of latitude, right? They sort of deserve to be called a triangle in this world because they're sort of made up of the curves that are as like as short as they can be, right? Like remember a triangle in our world, right? What's a triangle in our normal world? PQR. Well, it just consists like basically consists of three lines, straight segments, right? But straight segments are sort of like the shortest curves. These are sort of being built out of the shortest curves. So in the spherical world, this is actually like a triangle. Like in the same way, you know, in which circles in the taxi cab world look as like squares, in this spherical world, this something like that looks like this actually would be called a triangle by creatures living on the sphere. So this is like a triangle, the triangle PQR. But like there's like a simple calculation that you can make that sort of the angle between them at these vertices are actually all 90 degrees. Like that's not too bad to like, it can be shown if I gave you formulas for how to compute this. And so in this triangle, like the angles add up to 270 degrees. And we know in the normal world, what do the angles add up to? 180, right? So what can happen on the sphere in general is that on a triangle on the sphere, the sum of the internal angles is more than 180. That's not, it doesn't have to be 270, we sort of, but it has to be more than 180. So on the sphere, the triangles that you draw add up. Sorry, the sum on a sphere, the sum of the internal angles of a triangle add up to more than 180. Is that making sense? Um, can you still see this? I hope Canvas being down does not affect you being able to watch this. Can you still see me? Okay, so you can still hear me. Good. Now this, like, I guess I didn't have time to explain it today. We'll start this next time. But this is related to the fact that the sphere has positive curvature. So this, like, as we will see next time, this is related to the fact okay. So we'll talk about next time about what having positive curvature means. There's also a way in which you can have negative curvature. Okay. So we'll talk about this next time. So in general, like surfaces, like curvature can be like positive, like a sphere. It could be zero, like a piece of paper or the plane, or it could be negative, like what's called like a saddle or like a potato Pringles chip. And in fact, um, like the idea is like, for example, if you wanted to measure whether or not your space is curved, like one thing you could do is, for example, check this thing about the triangles. Like you would draw triangles in your universe and check if the angles add up to 180, more than 180 or less than 180, and that would tell you something about the curvature of the universe. In fact, this is actually Gauss figured this out, and he made expeditions to sort of measure the curvature of the Earth based on this fact. So you don't need to be like you don't need to exit the Earth to sort of try to detect whether or not you live in a curved space, because like you could do this test with the angles of triangles. So maybe just to finish today, I think videos can be fun. So let's just watch a quick video about this, like about cosmological consequences of this, and then we'll talk about that maybe later, another time with more time, more detail. Can everyone see the Firefox? We're used to. Okay. This is like a short minutes, 4 minutes. So
thinking of We're used to thinking of space as the emptiness in which things happen, like an empty warehouse ready to be filled, or a theater stage on which the events of the universe play out. But general relativity predicts that space is not just emptiness, it's a physical, dynamical thing. And that prediction has been borne out by many, many experiments. Space can bend because of matter and energy, curving the paths of objects that move inside of it. It can ripple with gravitational waves, and it can expand, creating more and more space in space. All of these seemingly different phenomena can be described by one idea: curvature of space, or space-time. In flat regions of space, like if there's no energy or matter nearby, objects traveling along parallel paths stay along parallel paths. In positively curved regions of space, like near planets or black holes, parallel paths converge, and in negatively curved regions of space, parallel paths, or even paths pointed at each other, diverge. But what about space as a whole? If space is positively curved everywhere, then there's only one shape space can be: a giant hyperspace potato. If you went in one direction for long enough, eventually you'd end up in the same place you started. If space is flat everywhere, its shape could be simple, just extend out straight into infinity. Or it could loop around in a periodic way, like in some video games. And if space is negatively curved everywhere, sports would be impossible. So which is it? There are basically two ways to measure the large-scale curvature of the universe. One is to measure the angles inside of triangles. If space is flat, the angles will add up to 180 degrees. But if space is curved, those angles will add up to more or less than 180 degrees, depending on the type of curvature. Cosmologists have done the equivalent of measuring our universe's triangles by looking at a picture of the early universe and studying the spatial relationship between different points on that picture. The second way to measure curvature is to measure the thing that causes space to curve in the first place: the density of energy and matter throughout the universe, which cosmologists have also measured. It turns out that in both cases, measurements show the universe to be pretty much flat, with a 0.4% margin of error. But before you get disappointed that we don't live in a cool cosmic hyper potato, let me tell you one big problem. The fact that we live in a flat universe appears to be a gigantic cosmic level coincidence. If the universe had just a little bit more mass and energy, space would have curved one way. And if it had just a little bit less mass and energy, space would have curved the other way. But we seem to have just the right amount to make space perfectly flat, as far as we can tell. This perfect amount is the equivalent of 5 hydrogen atoms per cubic meter of space, on average. Those big empty parts of space make up for all the atoms we have crammed in here around us. If instead there were 6 hydrogen atoms per cubic meter of space on average, or 4, the entire universe would have been a lot more curved, or a lot less. And we so far have no idea why our universe has the mass energy density it does. When it comes to the curvature of the universe, our knowledge falls flat. Hey, this is Henry. As you may have noticed, this video was a collaboration with my friend Jorge Champ, who does PhD comics, and Daniel Whiteson, and they have a new book out called...
So that was fun, right? So yeah, I think this is a good place to start. Next time we'll start talking about what curvature is. Yeah, it's fun, right? I like those videos. Short, but give you a lot of information. So next time I'll start telling you about curvature, and I still haven't told you how to relate it to the other characteristic. That's a pretty cool result of Gauss. So we'll see how that it all fits in together. You too, you too. Bye. Have a good one. Bye. I'll see you next time then.